Example 4. Consider the functions f of x equals x squared, g of x equals e to the x, and h of x equals the square root of x minus 2. Now we want to find the following. Notice that all the compositions that we're going to look for in this particular problem no longer have an x in the middle, which means we are no longer plugging functions into functions. Instead, we are looking for numerical outputs. We're plugging numbers into functions, and when we plug numbers into functions, we expect numbers as answers. So here, let's take a look at the first problem, f of g of 0. There's two different ways that we can complete this. We could find the composite function f of g of x first, like we did in the previous example, and then plug in 0. However, I'm going to go ahead and do it the alternate way. We have all the composition functions from before, so you can check your work to make sure you're getting the same answer by plugging the number into our composition from example 3. If we have a new composition where we hadn't done it before, usually it's a lot easier to find individual calculations and plug them into one another. What does that mean? So for the first example, I'm going to start by finding g of 0. I start with the innermost computation and I get that value out. So g of 0 means I'm going to plug in a 0 wherever I see an x. So I have e to the 0. And anything to the 0 power is going to give you 1. So if g of 0 equals 1, that means for my composition, I can then substitute in a 1 for g of 0. That means that I'm now looking for f of 1. F of 1 means I'm going to go to my f function, and I'm going to plug in a 1 wherever I see an x. So that's 1 squared, which is 1. And again, if you go back to the original composition, we ended up with e to the 2x. And if we had plugged in a 0 there, we would have also gotten 1. For the second problem here, g of f of 0, I'm going to start by calculating f of 0, the innermost function. F of 0 means I'm looking for 0 squared, which is 0. That means I can substitute that in for f of 0. That turns it into a problem where I'm looking for g of 0. G of 0 means I'm plugging a 0 into the g function, so I have e to the 0, which equals 1. For the next one, I have h of f of 3. So again, I start with my innermost function, f of 3. When I plug that in, I'm looking for 3 squared, which gives me 9. So I substitute in 9 for f of 3, and I get h of 9. H of 9 is going to give me the square root of 9 minus 2, because again, I'm plugging in the 9 for the x in the h function, which gives me the square root of 7. Now's a good time for a little caveat. The square root of 7, you should leave as the square root of 7 unless something or someone instructs you to round to a nearest decimal. The square root of 7 is an exact number. Once you put that into your calculator and turn it into a decimal and start rounding, it's more of an approximation than an exact number. So it's better to leave it as the square root of 7 instead of turning things into a decimal. Of course, if you're working on homework or on an exam and you are instructed to round to such and such decimal places, go ahead and plug in your calculator, but otherwise, leave it as the square root of 7. The next problem, h of g of 1. So again, we start on the inside and we work our way out. G of 1 means that we're going to take 1 and plug it into the g function. So we get e to the 1 power. Anything to the 1 power is just itself. So we just have e. E is a number. It's approximately 2.71, and it comes from a limit that we may look at later in the semester. So e itself is a number. So now we're looking for h of e. So that means we're plugging it into the h function, and we get e minus 2. And again, we don't want to change anything about this. This is an exact answer. We could plug this all into our calculator if we wanted to get a rough idea of what this number would be, but we can leave it as the square root of e minus 2. H of 6. So the first thing I need to do is calculate h of 6. H of 6 is going to give me the square root of 6 minus 2, which equals the square root of 4, and the square root of 4 is 2. Now I'm going to take that and I'm going to plug it back into h again. So now I have the square root of 2 minus 2, which equals the square root of 0, which is 0. So h of 6 equals 0. Now if I want to try f of 3 times g of 0, I want to find each of these pieces individually and multiply their answers together. F of 3 means I'm going to have 3 squared. 3 squared is 9. G of 0 means I'm going to be plugging 0 into my e function. Anything to the 0 power is 1. So I'm going to multiply my results. 9 times 1, which gives me 9. So in this last problem, I was finding each of those solutions individually and then combining them to get my final answer. Something really important I want to note here is that when we have a number in the innermost part of our composition, we expect a number as a result. When we had a variable or a letter in the innermost part of our composition, we are expecting a function as a result. So keep those things in mind when you're doing problems, because it's always a good idea to have a rough idea of what your solution should be before you even start. Example 5. Consider the table below, which gives values of 3 functions. We're going to use different compositions to find different outputs, similar to what we did in the last problem. First, I want to take a minute to explain this type of table in case you've never seen a table with more than 2 rows. So across the very top row, we still have our independent variable x, and x can take on the values 0, 1, 2, 3, and 4. Underneath that, we have f of x, and that's going to give you the dependent values of f of x if you plug each of those independent values of x in. Underneath that, we have the dependent values for g of x based on the independent values of x. And then below that, we have the dependent values for h of x, again, based on the independent values of x. So in evaluating any of these things, we're going to be referring to the independent value of x and then finding the correct function to plug it into to find the corresponding dependent value. So for example, let's look at number 1, f of g of h of 1. So like before, we're going to start on the inside and work our way out, which means the first step is to find h of 1. H of 1 means that we're going to go to the independent value of 1 and go down to the h function to find the corresponding output. The corresponding output is 1. So that means instead of h of 1, we're going to substitute in the dependent value we found, which was 1. This results in a new function that we have to evaluate. Again, we're going to start in the middle and work our way out. So now we have g of 1 that we need to consider next. So again, we're going to go to the independent value of 1, but now we're going to go down to the g function, which is the middle row, to get our dependent output. So g of 1 gives me a dependent output of 3. So I'm going to substitute that in. That means finally, I'm looking for f of 3. So I'm going to go to the independent x value of 3. I'm going to go down to my f function, which is the row right below it, and go ahead and find the dependent output for f, which is 0. So f of g of h of 1 finally gives me a numerical answer of 0. So I started in the middle and I worked my way out. Let's take a look at the next one. So now we have g of g of g of 1. So we start in the middle and we want to find g of 1. So we go to our independent value of 1, we go down to our g dependent value, and we get 3. So that means that we can substitute that in, and now we're looking for g of 3. G of 3 means we're going to go over to the x value of 3 and again go down to the corresponding g output, which is 4. So g of 3 equals 4, which means we're now looking for g of 4. G of 4, we're going to go to the x value of 4, go down to the g row, and we see an output of 2. So g of 1 gives me a final value of 2. What this is saying is if I had the g function and I were to compose it with itself 3 times, that my new function if I were to plug in a 1, would spit out a 2. So even though we don't know what that function is, that g of x function would have to compose itself 3 times, we can use this table to figure out what the outputs would be. So for the last problem, we're looking for h of g of f of 1. So we start by finding f of 1. So we go to the 1 value for x, then we go to the output for f, and we get 2. So now we have h of g of 2. So next we need to find g of 2. So we go to an x value of 2. We go down to the g value, which is the middle of the 3 functions, and we get an output of 4. So we substitute that in, and we have h of 4. So h of 4, finally we go to an x value of 4. We go down to the output for h, and we get a 1. So h of g of f of 1 is equal to 1. So with composite functions, if you have a table, you always start on the inside and continue working your way out until you've done all of the compositions. What should result finally is a numerical answer, since we're looking at numerical values. Example 6. So here is a practical example that you may have encountered at some point if you've taken any sort of physics course. So we have the formula K of C equals C plus 273. And this formula converts Celsius temperatures into Kelvin, which is a unit of measurement for temperature that is often used in chemistry and physics. We also have the formula C of F equals 5/9 times F minus 32. And that formula converts Fahrenheit temperatures into Celsius. So we use these to convert temperatures back and forth depending on what we're using them for and which unit it needs to be in. So for part A, we want to write a composite function that will convert Fahrenheit temperature to Kelvin. So since we ultimately want Kelvin, we have Kelvin as the outermost function. And in order to get to Fahrenheit, we need Fahrenheit to be the innermost part of our function. So we're going to do K of C of F, which means that we're going to be plugging our Celsius function into our Kelvin function. So that means we're going to go to our Kelvin function, and wherever we see a C, we're going to plug in 5/9 times F minus 32. So we result in 5/9 times F minus 32 plus 273. So again, I took my C function and I plugged it into the Kelvin so that my Kelvin will result from plugging in something in terms of Fahrenheit. Part B. Convert the boiling point of water, 212 degrees Fahrenheit, and the freezing point of water, 32 degrees Fahrenheit, to Kelvin. So that means that for the first part, the boiling water, I want K of C of 212 degrees Fahrenheit. So if I plug in a 212, I have 5/9 times 212 minus 32 plus 273. I'm going to carefully crunch that number in my calculator, and the result is 375 degrees Kelvin. I've successfully converted it by plugging in the Fahrenheit value to convert it all the way to Kelvin. Similarly, if I want to know the freezing point, I'm going to plug in 32 degrees Fahrenheit. So when I plug in 32 degrees, I get 32 minus 32 plus 273. I can see that this is going to be 0, which means that my Kelvin temperature will be 273 degrees Kelvin. So by setting up this composite function, I'm successfully able to go from Fahrenheit to Kelvin without having to go through the Celsius formula. That's one of the benefits of composite functions.